happy to have Dr. I'm very happy to have Dr. Jose Luis Ambite here. This is our first AI for Health seminar. Thanks to all of you who came out in person, and for those of you who are on Zoom, thanks as well, although you're missing the view and the lunch. Dr. Ambite is an associate research professor in computer science and a research team leader here at USC-ISI. His research interests include data integration, learning schema mappings, entity linkage, information extraction, databases, federated learning, and biomedical data science. And he's going to be talking to us today about federated learning and integration of biomedical data. Take it away.
Thank you, Mike. So I'm going to talk about our work on federated learning and that integration. And it's actually the work of a lot of people, not just me. I'm presenting it. What I'm going to present is mostly the work of Dimitri Stripelis, which is new PhD. He defended his thesis last week, and what I'm covering is mostly his thesis. So Dimitri was the kind of architect of the federated architecture, but then there are other people that have contributed to this effort. Mohammed and Sebastian and his student Thompson did a lot of the security that you will see later, and Greg and Roman did the protection against some immersive attacks and kept us kind of sane in machine learning in general. And then Paul Thompson and Nikhil and other people in Paul Thompson's group, they help out with all the neuroimaging data studies and their favorite neuroimaging neuroscience people. Okay, so this is the question that we wanted to address. Can we learn productivity data respecting privacy? And this is motivated for many reasons. We have particular interest in medical data, so you can imagine you have data at different hospitals, and you want to learn to predict some disease or some condition, say predict Alzheimer's prognosis from MRIs, something like that. But you don't want to share the data, or it's hard for you to share the data. And sharing data in general has become harder and harder. Here you may not be able to read this, but that's kind of all the places in the world in which there's some kind of data protection needs, from GDPR in Europe to many others around the world. So it's not only limited to the medical domain, but we're particularly interested in kind of biomedical data. So can we learn productivity data respecting privacy? And the answer is yes, we can use federated learning. And federated learning is a method to learn a particular neural network model without sharing data. The way it's done is that training is pushed down to data sources. The sources do share something. They show the parameters. These are the weights or the gradients, or the gradients from the neural network. But these parameters can be strongly protected, and we'll show in the middle of the talk so much protecting it through encryption and other more sophisticated methods like gradient noise, so kind of differential privacy. And the idea is that you have a global model. In this case, there are different approaches, but in the simple one, you have a single model. You're trying to predict one thing, like Alzheimer's prognosis from MRIs, and you have every site, think of hospitals, clinics, gets that model. They train locally for a little bit, and they share the parameters with the global model that aggregates all the local models, sends them back, and it goes through a number of federation rounds. It's called to converge to the final model, the performance. And even before I give you the details, let me tell you why we went to federated learning. And it's because you would do better if you join a federation than you just try to process data yourself. And it's basically because more data, you can reach more data through the federated learning system than what you probably can have locally, or you can convince other sites to share data with you. And these are simple experiments in which these are 8 different sites. And this is with a kind of this problem is brain age, which is predict the age of human brain from MRI. And you can think of it as a kind of nice biomarker of the health of your brain. So if your age of your brain from the MRI is actually older than your chronological age, you probably have some neurological disease. But it's also like a good test bed on to test your federated learning and deep learning systems. So here I'm showing 2 different scenarios. One is that you have these 8 sites, and they'll have the same data distribution, so kind of the same range of ages, and they'll have all the same amount of data. So here in the left. And if you do that, you can see that the performance that each site gets, and here the y-axis is the mean absolute error, so lower is better. And the y-axis is just the kind of the time that it takes to converge. So this is a convergence curve. And you can see, well, as the system trains, it gets better and better. But at each of the hospitals, at each of the sites, they only get this level of performance, about 3.6 or 7, something like that. But the federation, the community model, the one that is getting data from all the sites, even if the data is actually not shared, but it's kind of being learned through a neural network, gets a much better performance. So you get a much better neural network, a much better predictor of the prognosis of Alzheimer's, or in this case, the age of the human brain, by using the federation. And that's in this kind of benign environment in which every site is kind of more or less like the other, and they have the same amount of data. You have a more realistic situation in which different sites have different amount of data, and the data distribution at each site is different. So here maybe it's younger people, here's like older people, here's like a broader. we would find in a more realistic scenario. Then the performance of each site can vary a lot. If you're a small site with a little bit of data and you're far away from the global distribution, you're probably going to do terrible. And here we're testing over the global distribution because we want to have like a general predictor of age. And you can do terrible. And if you're the biggest site with the most data and kind of a good distribution, you still don't do as well as the federated system. So all sites should join the federation. Yes, join the federation. For background, federated learning has been applied in different environments. There are two main approaches, two main environments. One is called the cross-silo, which is the one we are particularly interested. And it's like kind of tens or hundreds of organizations, think hospital clinics. Generally, they're highly available. They're always on. They're connected to a high-speed network. They all participate in the federation when you're training. The other environment is the cross-device, and this is more like Internet of Things, the mobile devices. And here you can have like tens of thousands, millions, tens of millions of devices, and you're trying to learn from that very distributed sensors, very large number of devices. And here it has a different characteristics. The sites can drop out, the phone runs out of battery, the sensor runs out of battery. They have different availability, different communication costs. The techniques are similar, although these environments have these differences. I'm mostly going to be talking about the cross-silo device, but I think all the techniques that we have are also applicable to this other cross-device, although we have done less experiments on those. So how does federated learning works? As I said, you have different sites. Each site is think hospital. All the data is always behind a firewall, never gets out of that system at all. There's some code. There's some code that is going to train over that data, but never gets it out. But what it shares are these parameters of the network, like the gradients, pseudo gradients, the weights. And they share with a federation controller, some centralized site, that does navigation of the model. So each of the sites trains for a while, share the parameters, and they get aggregated. And often the aggregation is a simple weighted average. So it's a simple kind of aggregation of these models. And then that new model that has been computed as the aggregation of the local models gets sent back to its learner, and they start training from that point again over the private data set. This is this original protocol in which everybody trains synchronously, so everybody trains for a fixed amount of effort, say like 4 epochs. So you don't communicate very often. You can communicate kind of every few minutes or even more. It's not like a distributed learning in which you are communicating the batches. After you do some gradient, you communicate. This is kind of to decrease you don't have a lot of communication, and you train for quite a bit in each site. So that's a difference with distributed learning for those who are familiar with those algorithms. This was started by a group at Google, well, and others, but mostly the initial papers at Google in 2016-17, because they have this protocol, it's called federated average, because you just take the models and averages. There are many other models, and we'll cover some of them later. So what are the challenges of federated learning? Oh, yes.
What are the weights? How do you?
So the weights are literally, so a neural network is essentially a collection of matrices. And well, there are 2 weights. One is the W, is really like all the matrices of the neural network. And then the way that you weight each of those models, there are different algorithms. The most common one, the original one, is weighting by the number of examples. So if this site has 10,000 examples, and this one has 1,000, 500, that weighted proportionally to the number of examples. That's a typical way of doing it. But there are other methods, and I've discussed some of them, other variations that we have looked at later. Thank you for that question. I forgot to say that. Yeah, because, well, the number of examples is a proxy for the quality of the model that you're going to get, in essence. So you want to get that you want to weight the models that you trust more heavily than the ones that you know. Yeah.
Let's say we're talking about neural networks. So the assumption is that these different classifiers.
Yeah, these are neural networks. These are deep learning networks. Okay, so definitely learning in more general classical algorithms like distributed regression, but what we're doing is all neural networks. That's
okay. So the assumption is that they have the same architecture in terms of
yes, we assume that.
Hyperparameters and activation functions, so on, right?
Yeah. So in the simplest model, and this is the one that we're going to take for this lecture, this talk, is everybody is training the same neural network architecture. So there are other models that can do personalization. You can train part of the model. There are many variations, but in most of in all of what I'm going to present today is the same neural network for the same task. You can also multitask. We have personalization for each side. There are many variations, but for the rest of this hour, it's the same neural network. Okay, so what are the challenges? Again, you can have different communication capabilities in the kind of cross-silo setting, kind of the set of hospitals. This is really not a big deal because you have like good internet connections. But if you're in cell phones or sensors or cell phones, they may have different bandwidth. You have slow sensors, they may drop off. They also may have different processing capabilities. So each side may have like a latest generation TPU or GPU, and another side may have other GPUs or even a CPU. So they may process data at very different speeds. And also the data itself on each side maybe they may follow different data distributions, and also maybe structure on the different schema. And here's where the data integration comes, and we'll talk about that at the end of the lecture, of the talk. So as I said, communication heterogeneity, different communication calls depending on the environment. In the cross silo, there's some latency because maybe you have different oscillators at different across the world. We actually sent some proposals to have this kind of worldwide further learning systems. So you may have a site in Japan or in India. But generally, it's not too bad because they have high internet connections. But in the cross device, you might have slow connectivity, limited bandwidth, physical distance, or kind of more trouble. For computational heterogeneity, again, you have different processors. And this is you have different amounts of data. So if one side has a lot of data, it's going to take it probably longer to process. And another side has less data if they have the same processor. But there will be variability on the computational capabilities. And this is what happens. So you have a homogeneous environment, say 10 GPUs, 10 sites that each one has a GPU. Well, all of them are active. This is with the federated average, synchronous federated average protocol. On CFR10, which is a benchmark domain with a CNN, two-layer CNN, the GPUs are all happy and computing constantly. However, you have a combination in which you have 5 sites that are GPUs, so CPUs, and 5 that are GPUs. The CPUs are kind of doing as much as they can, and the GPUs are pretty much idle because they just finished their allocated work. In this, as I said, in this particular training policy, you train for a fixed amount of effort. So to do, say, 4 epochs for a GPU is really quick, but to do 4 epochs for a CPU takes a while. So basically, the GPUs are just waiting, doing nothing most of the time. It's not desirable. And this is what will happen. You have all GPUs, you converge quite quickly. You have this mixed environment with CPUs and GPUs. It takes a while to converge. And one of the major heterogeneities in further learning is the statistical heterogeneity and the amount of data you have. So different amounts, different heterogeneity of the data distribution. So we've done lots of experiments on different environments, and this is how they look. So this would be a data uniform and IID. Basically, every site has the same amount of data, and every site has a local distribution that corresponds to the global distribution. You can have sites that have different amount of data, and also they have a different data distribution. And here we're changing data distribution by picking the target classes. So this is a problem with 10 classes. It's like CFR10 in this case. So every site has only 5 out of the 10 classes. So if you think of a hospital environment, there's like one hospital specialized in some types of diseases, a different one one says like cancer center, so it's mostly cancers. Another place is like a neuroimaging center, so mostly kind of neurological diseases type of things. So this notation that we see later on an ID5 means that at each site it's only 5 out of the 10 classes, and here every site is only C3s out of the 10 classes. So it's a kind of hard problem because if you think of the kind of CIFAR10 domain, this CIFAR10 is recognizing objects in images, things like cats and dogs and trucks and cops and planes and birds. So you can see that one side has only birds and trucks and dogs, and the other side has cats and sheep and so on. So it's a hard domain to learn from, but that may happen. And in a realistic domain, in medical domain, again, it may happen because different sites have different distribution of patients in general. And this affects the learning. So in that amount, you have the same amount of data, this kind of a skewed amount of data, or this kind of power law that is, we put it to inspire this kind of long tail of science type of thing, that you may have many small sites that have a little bit of data, and you want to capture them. And then the data distribution itself that we're modeling with having different target classes per learner. And this is what happens. So in the kind of benign, nice environment, uniform ID, you get like a nice convergence curve. The power law actually doesn't hurt you that much because it's driven mostly by the bigger sites that have most of the data. All these experiments have the same amount of data, just distributed in different ways. But then if you get this skewed ID 5, it gets harder to learn and harder to converge. And the skewed ID 3 is a harder problem, it gets harder to converge. So this is kind of what happens in Federated learning. And you also use experiments in which different types of policies converge to different final amount and different rates of convergence. And that's kind of a lot of what we've been looking at. And just to see overall what's the span of things that we've been looking at, and I have to again to acknowledge Dimitri Stukelis, which is sitting right there, which is defended his thesis last week, and this is kind of his thesis. So we have this type of heterogeneities: the computational and statistical heterogeneities, the communication, the processing, the statistical, the amounts, and then the semantic heterogeneity, which links to data integration, which means that at each site, if these different hospitals, they probably have different storage devices. Maybe they all use whatever Cerner or Epic, some common, but they may have their own different storage of the data. Most importantly, they may have different schemas, so they may have represented in the same data in a different structure, and maybe with different values. So all the problems of data integration are still under the hood in Federated learning, and we've done historically a lot of work on data integration in an ISI. So we wanted to bring all of that into Federated learning. Okay, so let me tell you a little bit of training policies. And again, this is a very, very active area of research. There's lots of work. So we're going to just cover a little bit of mostly the work we've done, but there's a lot more. So in communication policies, you can have these basic methods like synchronous, asynchronous, or semi-synchronous. And this is like our method. So the synchronous is what I described. You assign a fixed amount of work for each site to do, say 4 epochs. So processing all the data set 4 times in neural network. And whenever they finish, everybody in the federation waits for the slowest learner to finish. And then they synchronize, do an aggregated model, a community model, a global model, and they send it back to the learners to train again. And that's kind of how it proceeds. And what happens if you have a very fast learner? Well, the fast learner finishes its allotted work very quickly, and then it just sits there doing nothing until the slowest learner finishes. That's synchronous. Asynchronous, there are synchronous protocols in which as soon as anybody finishes, so let's say we're here already, when this learner 2 finishes, it sends the local model to the controller, and the controller is going to compute a new community model using the latest local models from the other sites that it has available at the time, which would be this model here and this model here, which was last time it was communicated. And then in our algorithm that is kind of works surprisingly well, what we do is like we just work all the time. So as opposed to allocate a fixed amount of work, we say a fixed amount of time, and they say 5 minutes, and everybody works for those 5 minutes and sends the models when they are done. So there's no idle time. So what are the comparisons of this? What are the advantages and disadvantages of these methods? So the synchronous federated learning is actually simpler to analyze and prove theoretical properties of convergence and things like that, but it has this underutilization of resources. Problem things are idle. Asynchronous, there's no idle time, but if you notice when this learner, again, computes the community model, is using models that are kind of a little bit behind. No, they were the models that were computed a while ago. Like this learner actually has been processing the data a bit longer, but you just get a little bit older design. So there's a bit of staleness. And also it has a bit of more communication cost. But and then our approach, it has no idle time. It actually oversamples the fast learners, which that seems that it would be a problem because you may bias the federation towards the data that sits of the fast learners. However, experimentally, it works quite well. And it's the intuition, at least for me, is a way of kind of inside domain transfer. So the fast learners are kind of getting a better model quicker, and are kind of teaching the slower learners. And that kind of mixing actually does for fast, lets you to achieve faster convergence, and we'll see in experiments in a minute. Okay, so that's the communication policies. And then the model mixing, and again, there's an enormous amount of work on this, but you can think of what the controller is doing, the way it's kind of aggregating the models, and also what the optimization of this local learner does. So there's a global optimization, a local optimization. For local optimization, you can do like a vanilla stochastic gradient descent. You can do something called FedProx, which is a proximal algorithm in which each learner you're trying to penalize if it moves too much from the global model. So you're trying to kind of make sure that the deviations from the global model kind of pay off. In a sense, it's like a type of regularization. And then you can do momentum, which also has a flavor of that, in which you don't move too quickly. You have like inertia, so when you change your gradients, you also take into account like the previous weights, so that you don't move too fast, like inertia in physical systems. So we tried this like with the different algorithms, like synchronous algorithms and semi-synchronous, and then the asynchronous algorithms that do the same thing. And the weighting, I said, most of the time is weighted by the number of examples, but you can also weight by the time elapsed. In these asynchronous models, you can say how stale the model is, and you can weight inversely to that. So you would prefer like more recent models, and also by the number of work that you actually have done. You can compute how many batches you have processed and weight based on that sort of batches. Okay, so how well does this work? So here I'll show you quickly a number of results. And I mean the bottom line for different environments. So here you have this data, same amount of data and uniform. And here it says IID5, so this is only 5 out of the 10 classes in CIFAR 10, which is displaying 10 types of objects in images. And this is 3 out of the classes. So going here to the left is more non-ID, it's harder to predict. And also going down is more skewed. This is like a moderate amount of skewed, and so this is very, very skewed. And as you can see, well, first, the blue lines are kind of our algorithm, the semi-sync algorithm that experimentally performs really well, converges quickly and to a high accuracy. In this case, so here, the left side is, the y-axis is accuracy, so higher is better, and the y-axis is time. And as you can see, some of the policies, in some of the models, they take a long time to converge, or they won't converge at all. And in general, our policies are either the same or better in rate of convergence than other algorithms. This is with the x-axis as time. You can also see a number of lesson rounds that is equivalent to the communication cost, so how many models are exchanged to converge a particular level. And again, you get the same thing. We kind of converge quickly, given the number of models exchanged, and other systems have a lower rate of convergence or converge to a lower value. We've done this in many domains. In CIFAR 100 is the same things. 100 types of objects in images. It's a harder domain. And here you can see a bit more of the difference. We did some kind of, and again, this blue line is kind of our method, tends to have faster convergence. We did something like an adversarial data assignment in which we put the most of the data in the slow learners and see what happened. It's kind of evil, but actually Cyrus Ahali suggested this, that we tested and it actually worked well. So this semantic algorithm is still, even if it has the slow learners, because you get this kind of inter-domain transfer between the learners, it still kind of has fast convergence compared to the algorithms. Another domain, standard MNIST, kind of more of the same thing. We have fast convergence, and sometimes we converge to a higher value, at least in this kind of range that we, maybe the other systems eventually converge to the same one, but we can run that long. It was only 10,000 seconds, so it's a long convergence there. Yes?
So you're saying that you get better results, or somehow you're getting faster convergence, whether you're giving more data to the faster learners or slower learners?
Well, so we take the distribution that the Federation has. So everybody in any of these experiments, so the data distribution is the same for every protocol. We're just testing how different protocols behave in a different environment. In ours, my intuition is it works better because this kind of the faster learners teaching the slower learners type of thing. This kind of inter-domain transfer, inter-learning transfer. But there's no data transfer. It's just the weights and the way the aggregation happens. But anyway, all this was like beneficial domains for people who are interested in medical domains. We are interested in medical domains, so this is the experiment. So much experiments that we've done on actual medical domains. So again, brain age. If you have this kind of benign or this, everybody has the same data distribution, and every site has a local distribution that mimics the global data distribution, and you test on the global data distribution. Even if you have different data amounts per learner, you get this behavior in which here the red line is a centralized data. It's like if you have convinced all your friends to give you the data, you analyze the data locally, which is probably the best you can do. How does that compare with a federated learning approach in which nobody shares the data? Well, this is great because you can have the same performance. You get the same error in the federation with the kind of the right algorithm. Okay, you can see this green line. You get the same performance pretty much as centralized. So this is kind of having your cake and eat it too. You don't share the data, but you get the same performance as if you had shared the data. Okay, this is great. Does this happen all the time? No, it doesn't happen all the time. You have a hard domain in which things are very skewed. You have sites with different data distributions. You have different amounts of data. The federated learning may have a gap with respect to the centralized. So the centralized system may have achieved a better performance. But the hope here, and actually we're running experiments to test this, where are the trade-offs, is that you may be able to reach more sites if they don't have to give you your data than if you have. And we have some experiments I don't want to send today, but at some point maybe you get twice more data in a federated system than the centralized. You may be able to get the same performance anyway. So the hope of federated systems is that you may reach a bigger number of sites, therefore much more data, and that may give you a better performance system. In any case, if people are not giving you the data, well, there's no way you can test it. Here we had all the data because we took MRIs from the UK Biobank, so we have 10,000 MRIs, and we could distribute them any way we want, and we could test the comparison, the centralized and federated. Okay, and in more real cases, this was predicting Alzheimer's disease status from MRIs from 5 different sites. And there are these are the three, again, these are all data we had because we want to compare with centralized, but here we put ADNI phases, ADNI 1, ADNI 2, ADNI 3, 3 different sites. OS is an able, so there were 5 sites total. Here you can see the amounts of data were kind of pretty different sizes. But the beauty of this experiment was that when we put everything centralized and we tested the accuracy, position of recall, F1, carrying the curve, and so on, the performance of the centralized system with all the data and the performance of the federated system over the 5 sites without sharing the data is essentially the same. So this is great. This is one of the cases in which, for this task, we can achieve the same performance as centralized. Okay. As an aside, we're also interested in efficiency. So again, most of our work has been on the cross-silo setting, but we're also interested in maybe moving to sensors. It could be biomedical, like personal sensors or the type of sensors. And so we look at what was the energy efficiency. And here is a simple experiment, but basically by the fact that we can converge faster, essentially we burn fewer energy. We take less time. So this is a busy plot, but what we are doing here is we define a level of accuracy that we want to reach in different environments, uniform ID, SQ non-ID, and so on over log. A given accuracy level, we chose these accuracy levels based on accuracies that most of the systems could reach, because sometimes they don't reach that accuracy. But if you do that, our algorithm can be up to 9 times more efficient in energy than kind of the baseline algorithm. Again, I don't want to read too much, but having fast convergence can also help you save energy. And we also look at other ways of improving the efficiency of resources. And again, this is also intended for small devices, in which you may or may not know that neural networks are very highly overparameterized. They have many weights, many parameters. But you can extract a very sparse network out of that dense big network that has the same performance. So we wanted to explore that in the federated learning system, in the federated setting. So we did some specification, also known as pruning, in which you remove parameters from neural network model, but maintaining the learning performance. So you get a really big network, and then you have a very sparse network that performs kind of the same. And the idea is that this sparse network, you may be able to deploy in a small device or a device with limited computational resources. There are two types of pruning: structure pruning and structure pruning. We looked at the structure pruning was easier to compare with other systems. And this, what you do is you remove the weights that have a small magnitude. So you have a big network with like millions of parameters, and then you put a threshold, and the parameters with a small magnitude, you literally make them zero. You kind of zero them out, and make all these matrices very sparse. And you can get very high levels of specification, as we'll see in a second. There's another type of pruning that looks at pruning blocks of parameters. For example, you have a convolutional filter. Maybe most of the values of the filter are small, then you remove that filter. That's a bit better for like the hardware implementation, but just for comparisons, we just look at unstructured pruning. But we plan to look into the structure soon. So we look at some different approaches to pruning that have been in the literature. So you can just prune an initialization and then use the federated learning normally. You can do the federated learning all the way, and then the final model you prune. Or you can prune during training in a couple of different ways. One is you train locally, and then you submit the data to the sites. To the controller, and then the controller prunes the model, and then sends the pruned model back to the learners, and this kind of keep specifying the model as you train. And another one in which you again you prune locally, and then you send the prune model to the controller that aggregates the model using some a majority vote on which weights to keep. So if you do that, and you compare all these different algorithms. So here the spread X is the algorithm without no pruning. So here on the X-axis is the amount of sparsity, how many weights have you removed from the network, and in the Y-axis the accuracy, higher is better. So if you don't remove anything, that's generally the best you can do. That's a great performance algorithm. And then different algorithms have different characteristics. And here we're going from 80% pruning to 99% pruning, which is basically keeping only 1% of the parameters. But we can keep almost the same performance as the model without pruning. So you save 99% of the size of the network, and you keep the same performance. And we've done a lot of experiments on different environments. This left column is IID. This right column here is non-ID. This is 10 clients, so kind of this cross-silo approach, like certain hospitals. This is a more like closed device in which there are like 100 clients. But when you have many clients, I forgot to say that you sample. You don't try to aggregate a million models from devices. You just sample from those devices. And here the prediction rate is 1%. So essentially, we sample 10 learners every time we aggregate. And it's the same picture. I mean, the details, you don't have time to go to details, but you can see that this is the point of the model without pruning. This is like 90, 95, 99% pruning. And you can see that our approaches, that is green stars and squares, are maintaining that performance without, and the other approaches kind of collapse when you go to high levels of pruning. So this is nice. Like this is what is happening. So this is the way that our left axis here and our right axis. The left axis is the accuracy, and the right axis is the amount of parameters. And you go from 120,000 parameters, where you can read that, to things like 10,000 parameters. This is kind of the specification rate in our kind of progressive classification approach. And this is how it converges. And this is the convergence rates for many different algorithms. Okay, so that's kind of the basic idea. There's a trade-off between the accuracy that you want to keep and the amount of specification. So you can go from like 1.6 million parameters to say 80,000 with pretty much no performance gain, and you can go even to 16,000 with a little bit of more performance here, like 0.05, but maybe that's worth it. Maybe you want a model that's really small. It's like 56 times smaller than the original one, and it still has pretty high performance. And we've done this in different domains, cifra 10, cifra 100. Again, you can get this kind of reductions of like 15 times, 60 times without a lot of hidden performance. We also done it in brain age to biomedical domains. And here, again, you can see that at 85, 90, 95%, there's pretty much no decrease in performance. So here, again, lower is better. In this case, the error is kind of the same. Then when you go to 99%, there's a little bit of increase in the error, but it's not too much. And you've decreased the number of model parameters in the model significantly from like 3 million to 30,000. So it's a much more sparse database. Okay. Okay, so I told you about filter learning, different training policies, different things you can do, like make the model small. And I said it was secure. So let me tell you a little bit of the security. So why is this secure? So again, no data leaves the site. Before we leave the parameters, you can say, oh, I can have the parameters. Just listen.
Is it okay to interrupt that?
Yeah, no, sure.
So just on the model itself, I was wondering, this is maybe firstly discussed in the past. I'm trying to understand, like, is there a good theoretical characterization for why federated averaging done the way this is being done does better than SGP? Because my understanding is
no,
that
SGP. I mean, so federated average. So in a sense, this federated average is kind of a poor man's SGP. So you're doing local SGP, and globally you're also kind of doing SGP, but you're kind of weighting by the number of examples as a way of kind of weighting the gradients.
Right.
But they're different algorithms. There are algorithms that try to correct for the bias of each local site. There's quite a bit of work, both some theoretical and also kind of experimental.
and there is like some complexity separation you can establish in terms of convergence.
Yeah, you can do convergence proofs of. The other thing that proofs can tend to be loose is like, okay, I kind of converge more or less in the same ballpark as like a normal SGD if it was not distributed. But when you get to these very complicated domains with like different skewedness, different data distributions, that's really hard to analyze theoretically because you have to make kind of hard assumptions of the distribution of the data to then realize how that affects the grades are computed and how biased they are. It gets pretty hairy. I'm not a theory person, but that's kind of, people have done some of this research. But a lot of the theoretical approach is more in the kind of synchronous federated average because that has a much clearer correspondence to the classical SGP. And also, I mean, I didn't make this super clear, but this is different from distributed. There's some people that do distributed SGD. You have a cluster of I mean, people do that when you have a cluster of GPUs. You can distribute things, and you can prove higher guarantees if you have more communication. So if every site gets like a batch, and then you get it back, well, that's kind of SGD by itself. But that assumes that you can control where to allocate the data in the GPUs. That assumes a lot of control. Here, you're assuming that you have no control over the data. So data is whatever it is at different sites. So if there's a hospital, they have the data they have. It's not that you can sample it in an empirical way. But the sampling just is quite different from the centralized case. In centralized, you can sample completely. You have control of the data, you can sample it any way you want, in a random way generally, which is the best thing. But if it is distributed, it is following whatever distribution it has. So you cannot do that kind of random sample in the same way.
So there's a question from on Zoom. It's one of the major factors that go into determining Alzheimer's disease. How we can capture those in the machine learning models.
So I've some examples in which we're mostly doing MRI type of data, but we also have, obviously there are other kind of type of information that you know about, from the demographics to age, sex, other type of biomarkers that you may measure. So you can have neural networks that capture both the imaging and the other kind of structural data. And we actually running experiments on that as we speak. I hope that answered the question. I don't know if that was the.
Well, since it was from the web, I'm not sure, but I think they were getting it more. What can you pick up in the image, whether it's brain age or other?
So it depends on the disease. I think Alzheimer has this more kind of effects over the whole brain. So the neural network is kind of picking up on those changes of the reductions on the hippocampus or whatever it is. I guess I'm not a neuroscientist, you should ask Paul. But the neural network is picking up on that. And you can get pretty high precision, like 80% and higher precision predicting. But different, I mean, we've done experiments with Parkinson too. Parkinson is harder to predict. So we're running these experiments. Okay, let me tell you a bit more of the architecture. Okay, so I said that it was a secure system. Again, data never leaves. And when these parameters live, these weights or pseudo gradients live, we encrypt them. So outside of the hospital, well, the only thing that gets out is the encrypted set of numbers, these encrypted matrices. However, the aggregation of the models, which is the simple weighted average, it turns out that it can be done under encryption using a method called Federated, fully homomorphic encryption. There are other methods, but we've used homomorphic encryption. Actually, Sebastian, who is here, is one of the people that actually help us incorporate the encryption into the system. So site trains locally where private data, encrypts the models, send it to the Federated controller. The controller aggregates all these encrypted models. And so even if it's breach or this controller was breach or anything was trying to inspect the data in transit, they only get encrypted data. Then they send back the encrypted global model to its learner, encrypts it, and trains locally. And you would say, well, is that very expensive? No, this is the kind of the beauty. We work quite hard. We use an existing existing fully homomorphic encryption method called CKKS, but we also optimize it. I mean, Dimitri and others actually had to work to make it more efficient. And we can do it with very low overhead. So this convergent graphs for brain age, what they show is that pretty much the encrypted and non-encrypted algorithm works the same, converges to the same, in this case, error, so very low error. There's no difference between with or without encryption. And these like two vertical marks you see here is the time it takes to do 20 phase on routes. And that's why we get this 7%. So you can get encryption and pay a very little overhead on time. So you can have really a secure system that is practical. So we did this in brain age. We've done it in other domains. This is again in CFR10. There are actually 3 lines here. You don't see them very well, but it's because the 3 lines are one on top of each other. And here you can see a little bit that one of line was taking longer. That was before we told Dimitri and Hamza and others did some optimizations, and now it's about 7%. So great. We have a system that trains, has fast convergence, can predict useful things. It is secure from outside of Federation. But if you are following closely here inside the learner, the global model was decrypted. So somebody, an insider that maybe is curious, can try to attack that model to learn something about the rest of the Federation. So we wanted to prevent that too. And in general, we're not, so this is kind of the attacks that you can do against the Federation model, Federated model. So I think with the encryption, the homomorphic encryption, data is really safe against attacks from outside the Federation. I mean, we have like HTTPS from the communication, we have encryption, so the version controller gets compromised. Outside the Federation, I think is very, very secure. But they have this inside attack, and we're following an honest but curious model. Sorry, honest but curious attack model. We're not looking at adversarial attacks in which one is trying to poison the learning system or kind of poison the learning by data or by modifying the gradients arbitrarily. We think that that's not very likely in kind of a research study or consortium of hospitals that we think that somebody is going to join a consortium and kind of trying to destroy the Federation out of spite. Although we have some work on that. But the one that we thought it was more plausible is this kind of honest but curious. And there are 2 things you can do. You can do a model inversion. Is that these deep learning models sometimes memorize data, aren't they? So maybe somebody can try to recover some image of somebody that was at a different site. This actually doesn't work very well, the kind of straight model inversion in the Federated learning environments that we look at, because every site trains over many epochs. And the model that a site gets is the model aggregated from all the aggregation of all the local models. So that kind of local memory is kind of gets destroyed. So this is not a very successful attack. However, another type of attack, as I will show you in a minute, is actually very successful. And that's called a membership influence attack. And this idea is that you have a site that participates in a federation. Let's say Abigail is a neuroscientist, and she took an MRI of my brain. For a good reason, I bumped my head, she took an MRI of my brain. So she has my MRI for a perfectly legal reason. But then she also participates in a federation that studies something sensitive, like HIV in the brain, or schizophrenia, or something like that. And she doesn't need to know that they participated in those studies. However, if she has my MRI, my local data, she can probe the network that she gets from the federation and tell they participated in those studies. And that's kind of an information that she shouldn't know. That's kind of a privacy violation.
I'm sorry. I apologize.
Oh, it's okay. Well, you are curious anyway.
Yeah.
Who knows? Yeah. Okay, so how do you attack these models? So once you have the model, you can look at all kind of features inside the model, like the activations, the gradient magnitudes, all kind of things. This is this is primarily the work of Gupta, Breguestek, and Dimitri, in which you can do these inference attacks. And this is what happens. Like, they are incredibly successful. So you have one of these nice environments, this uniform ID, so everyone has the same data and same distribution. You can tell that some piece of data you have was used to train the federation with like 0.75, almost 0.8 accuracy. So these attacks are very successful. I guess it's similar to the attacks that, like in 2008 or so, I don't know exactly. There was attacks against aggregated data in genetics, which people were posting aggregated results from genetic studies, like GWAS studies, and then somebody figured out how to, if you had somebody's DNA, to know if they had kind of participated in the study. So this is kind of the neuroimaging version of that. But it's surprisingly successful, in particular in this kind of environments. If you have these skewed environments, non-ID, the attacks are less successful, but it's still something that you want to worry about. At least we did worry about it. And there are a couple of solutions. One that is similar to differential privacy, but it's not on the data. You don't jitter the data. What you do is you add noise to the gradients, and you can add noise to the gradients in a kind of blanket way. And then Umang, Gupta, and Breguestek define a method called unique gradients that doesn't add noise everywhere, but it picks kind of the right gradients to add noise, so it's more subtle. And you can defeat attacks. And this is how this attack accuracy curves look like. So there's a trade-off between what is the level of vulnerability that you want to have and the accuracy of the system. So here in the top corner is the model that you have the best error rate. So here lower is better. You want to be in this kind of lower left corner. The model without any definition, any change has the best error rate, but it's also very, very successful to attack. It's susceptible to attack. But then you can add some kind of noise, and you kind of work this kind of Pareto curve and say, well, maybe I'm willing to give up a little bit of error, but I'm reducing my attack surface quite a bit, or maybe you want to be here. So this is something you can choose. And this is from a uniform ID model. This is uniform non-ID, where you can choose essentially what you want to be. So maybe you want to be here. You gave up a little bit of error, but you are very impervious to attacks. And again, these are not necessarily easy attacks, but if you want to be comprehensive, you may want to protect against this. We also showed here the specification by itself actually seems to add some protection. So having one of these small models generated by our progressive specification gives you some level of protection. But if you want a more thorough protection, you may want to add a bit more noise to the gradients. Okay, so I'm getting, I think, close. So we have, Dimitri has this very comprehensive framework. This actually works, it's very solid at this point. It's containerized, can be deployed. I think soon will become, we have an open source version of this. And this is what everything I talked so far. We also, Dimitri and another student, again, did other work optimizing the version controller. And we compare with other existing frameworks for data learning, and they can aggregate a lot of models faster. So here, lower is faster. This is the aggregation time, federation time, encryption time. So we can converge faster just because of the implementation itself. And we will have hopefully soon a paper on this that compares against more models, more federated learning frameworks. So that's what was quite a bit of engineering into the system. Okay, this is great. So we have a system. If you want to do federated learning, please talk to us. We'll be happy to do this federated learning problems with you. Unfortunately, I only talk about half of the problem. And I only have 2 minutes, so I'm going to be quickly in the rest. But I've talked about the federated learning part of it, but the data integration never went away. So most people in federated learning assume that they get the data at the different sites with the same shape. Again, if you get images or you get maybe they are the same, there's still some issues that I'm going to talk about. You have images in different scanners, you still need to do some kind of harmonization about that. But most people assume they're getting the kind of the same type of images, the same type of data. But if you have structured data, and somebody asked about this online, you really want to have to deal with all the heterogeneity that comes with integrated data from different sources. And again, we've had a long history of data integration work, and it doesn't go away here. So you may have different type of storage engines, different databases, different systems, most importantly, different schemas, different values, normalized values, missing attributes. Again, it's an example, just a notional example, like you have some tables, somebody has a relational database, others may have JSON, may have different types of database on this Postgres system versus MongoDB. Again, in general, the issue of having different data sources with different structure of the data. So we propose an addition, an architecture for a harmonization of federated learning, in which you have, like, each site has its own local databases, and you're going to build a common schema across all the sites. But that common schema is going to be enforced in a site-by-site basis using a technique that comes from database theory world and data integration world called schema mappings and query writing. So you're going to define how the data of the source maps into the common schema using the schema mappings. And then you're going to get the data that will be the input to the machine learning problem through query writing. And while you are doing that, you're going to kind of normalize the values so that everybody, if one site measures weight in kilograms, another one in pounds, they are both in kilograms, or these type of transformations. And then if you're missing data, we can also add imputation of missing data to the framework. And there's a lot of work that has been done in data integration literature on how to do this in a formal way. I will just give you an example of how these things look like. So this is it's probably should be a whole lecture by itself, I mean, this whole class by itself, talk by itself, but these are formal schema mappings. What you do is you have different sources, you define a global schema. You say maybe you have some subjects and have some demographic properties. You have the clinical data, and maybe you have some visits and some at some time. So it should be like some time, some assessment. This is the Montreal assessment for Alzheimer's. Some diagnosis, maybe some imaging data. Again, these are notional examples. And the way you have different sources that have different structure. So you have a source that has the date of birth and sex and ethnicity, visit. They don't have the mocha, but they have the MMC. They have some kind of local diagnosis. They have some MRI. Then you can do transformations that you can maybe simply compute the age from the date of birth and the visit time. So the age of this is the age of assessment. You can impute. So maybe you're missing. You didn't have the mocha, which is maybe the preferred assessment that you want, but you have the MMC, so you can impute the value of the mocha from the MMC. Maybe you can impute a diagnosis. There was some missing diagnosis, and that creates like a normalized input, a normalized schema, targeted schema for your data, and each learner will get the data it needs to the input to the neural network as a query over this normalized schema. And it's kind of the formal way of doing it. Again, for those who haven't seen this type of rules before, maybe they look a bit complicated, but are not. Essentially, this left-hand side of the rule is like a query that you're running. The query is accessing data from actual sources and doing some kind of algorithms or procedural attachments to these rules that can do normalization and imputation. So in here we're imputing again the mocha from the diagnosis, and this is ICD-10 codes. maybe, I guess, our diagnosis we like in the global schema to have, in the normalized schema to have ICD-9 codes. So here we're relating the local diagnosis to ICD-9 codes, the normalization process. But you can define the normalization through this type of rules. And then when you want to run, you want to get the input to the neural network, you just send a query over this virtual global schema. Then this query gets kind of executed. This gets translated to another query that is going to access the actual sources like S1 and S2, S3, and so on. And it will invoke the right additional functions like imputation or normalization and so on. And that's what you would get. Just a very quick thing over imputed data. Generally, as you know, if you are missing data, you can just remove the tuples, or you can try to impute them. If you impute them, you tend to do a little bit better. So this is like this cross here is without removing tuples, and these other points are different types of imputation, and you can see that this is higher than this. Here is error, so lower is better. And we have incorporated that into the architecture or in the process, in which you have the local sources at each side. They're going to have these schema mappings. They're going to get the data through this query writing process. And then for every learning problem that you want, you would define the neural network that you want to train in, and you want to find the input to a neural network, and that's a query that goes against these sources. Again, these are the local sources at one side, at one hospital. You want to release for efficiency, and then you train in the ways that I just described overall. So that's it. That's our federated learning and integration architecture. So the first part of federated learning is completely available right now. That integration, we're still kind of working on it and integrating all the infrastructure, but we have lots of work on mediators and video integration systems before. And we think this is kind of ideal for biomedical domains. No? If you want to do prognosis or diagnosis, treatment, and see the effect of drugs. So we're interested in looking at amyloid plaque in the brain as a way of predicting the effect of different drugs. And as future work, again, we want to keep working on different algorithms to improve the performance of learning systems, test different federated learning frameworks that now several of them integrate the query writing and the imputation. There's some kind of technical problem there. Do imputation in a federated way. That's kind of quite interesting. Also measure the value of data. You have different sites. You have 10 different sites. Which one of those are giving you the most bang for your buck you want to have? And I see we have a bunch of publications, and I hope lots of people that work on this. Thank you very much. And I need to finish. Time for questions. If there are questions, happy to answer.
I was just curious on the last part of schema alignment. So there seems to be also like an entity resolution problem in there, right?
Yes. So there are private recordings across sites. So you have data from the same subject distributed among different hospitals. Then you want to make sure that you can align those subjects, and you can try to do that in a private way, which
I mean, not just private going into it, but even in the plain text.
So yeah, so that's this is kind of how do you entity linkage or entity resolution across different sites. There's a smaller problem, which is the normalization. Inside one site, you may want to normalize to like ICD-10 codes or something like that. That's also can be cast as a type of. But that's a simple one. The harder one is to do private linkage across sites. And if that happens, then you have to do a different type of federated learning. So most of what I describe is called horizontal federated learning, in which you assume you have like different patients at different sites. It's like you have a big table, virtual big table, but you partition it horizontally, so you have kind of the same type of data on every site. If you have data for the same patient across multiple sites, then you have to do a different type of training, because the neural network only gets part of the input in one side and part of the input in another side, and then the training algorithm and the aggregation algorithms are more complicated. And let's work on that, but there's some work in the literature on this kind of vertical federated learning that we're actually interested too. But we're focusing on the simpler one, which is the horizontal partitioning. And yes.
This is it's just a high level question, but when you're combining, because you're combining data from all these different sources with states, multitude of different factors that can differentiate the data. Are you kind of more robust in terms of training your models to like less overfitting is happening, and so you're able to get good, better estimates of your performance with smaller amounts of
So we haven't looked into that a lot. So I think let me paraphrase or rephrase what you're saying. I mean, that is hope that often in machine learning you think like random forests. Like you have many small models, and this kind of evolution of small models that are maybe biased to give you like a better performance globally. We haven't really thoroughly explored that, but it doesn't quite happen, at least what we've seen so far in other books. Because when you do random forest or other algorithm like that, in a sense you have control of the models that you can generate. You can choose how to create those each tree, in so that you have like a nice distribution overall. Here you don't have that power because the distribution is given to you and it's fixed. Like it's whatever exists at each of the sites. So you don't have that same. We did early on. We did some experiments on comparing federated learning with an ensemble. So what if everybody does its own best local model, and then you do an ensemble of the models? And in the early experiments that we did, the federated learning model was better than the ensemble model. I mean, I don't know if maybe there's more ways of doing ensembles better, but when initial experience that we did, the federated learning, that is kind of training with all the data, but kind of distributed, was getting a better model than doing an ensemble of the local models.
Okay.
I mean, that also has to say with, I think, what you're saying.
Yeah, definitely.
There was a question online, and it's referring back to an earlier slide, and it's a subscript. So, was the parameter P sub k determined by the data sample size only, or some other factors involved?
Yeah. So in the kind of federated average algorithm, and in many of the experiments that we've done, we weighted the local models based on the size of the data at each site. So it's basically the amount of data at each site. But there are other. I mean, I think we have other work that I didn't describe today, in which we actually evaluate its local model over a whole validation data set, and we see the performance of this validation data set, and that's the weight for those models. So in a sense, maybe you have a small model, a few examples, but the problem is not that hard. So even with those few examples, you still have a very accurate, high quality model. So we did some experiments, and again, I don't know if I have maybe over time, in which we weighted by the actual performance of the local model, and you can do things like that. And in other of the examples that we had in FedAsync, they're weighed by the kind of staleness of the model. So you can use other types of weights to weight the models, but most of the work is done on this kind of number of samples. But you can do other things like staleness, actual accuracy, actual performance of the model. I hope that. I mean, I think, I don't know if I can talk, but I hope that answered the question.
All right, we're about 5 minutes past the hour, and lunch is here. So let's thank the speaker and have lunch.